Welcome to the ENME 351 video lecture series. This is part one of a two-part installment on alternate actuation. This lesson focuses on stepper motors. DC motors are great if you want to operate a motor continuously. These motors provide a constant speed and torque. However, if you're interested in an application requiring position, then a stepper motor is going to be a preferable means of actuation. There are multiple types of stepper motors. These include the permanent magnet or PM motor, variable reluctance motors or VR, as well as hybrid stepper motors. In this lesson, we'll focus on these permanent magnet motors. So stepper motors are enabling us to achieve discrete steps in the actuation of our motor. Unlike the DC servo motor, where we have a sensor to describe the position of the motor, this capability to provide discrete steps in rotation is built into the stepper motor. The fundamental layout of a stepper motor begins with the rotor, and the rotor has poles. So here a single north-south pole. And then we have coils attached to the stator. These coils are hooked together such that we would have A and A prime. So the equivalent circuit would look like this, where we have A and A prime connected in series, and thus we have a single current going through both of these coils. There are typically multiple coils on the stator, and we also refer to these as phases. So shown here would be a two-phase stepper motor, and the second coil would be labeled B and B prime. And here would be the equivalent circuit for B and B prime connected in series. Thus the fixed component, that'll be the stator with the stator coils, and the number of stator pole coil pairs, so A and A prime would be one pair, B and B prime would be another pair, that's going to describe the number of motor phases. So thus we have two pairs in this motor, and this is a two-phase stepper motor. The basic idea behind the stepper motor is that we run a current through these coils such that we set up these poles. For A, we have a south pole, and for A prime, we have a north pole. And as a result, the rotor will now line up with the coils on the stator. So let's take a look at the fundamental operation of a stepper motor. Let's begin by sending a current through the A coil. So a current will flow from A to A prime, such that we set up a south pole at A and a north pole at A prime. As a result, the single pole rotor shown here will align itself in this direction. And it's also important to note that in this case, where there is current through the A coil, there is no current through the B coil. So this is step one of the motor operation. And for step two, we'll send a current through the B coil, here from B to B prime. As a result, B is now the south pole, and B prime is now the north pole. And in this second case, there is no current through the A coil. As a result, the rotor pole rotates to align itself to the magnetic field. So by changing our current from a current through coil A to a current through coil B, the rotor has rotated one step. The third step in the stepper motor operation now has a current flowing backwards through the A coil. So current is now flowing from A prime to A. As a result, A prime is now the south pole and A is now the north pole. And once again, we have no current through B, and the rotor now rotates through another step to align with the magnetic field. And then for the fourth step, the current is flowing through B in the backwards direction, so from B prime to B. This sets up a south pole at B prime and a north pole at B. And since there's no current through A, the rotor rotates through another step to once again align with the magnetic field. So for this particular motor, we have two phases with one pole on the rotor, and there are only four steps in the operation of this motor. So we could position the rotor of the motor to four different positions, each at 90-degree increments. So thus, the number of steps that the stepper motor can provide is going to be a driving characteristic for the particular stepper motor I choose for my application. To calculate the steps per revolution of the motor, we'll define P as equal to the phases of the motor and N poles as equal to the number of magnetic poles on the rotor. And so the steps per revolution, we'll call that S, where S is equal to 2 times P times the number of poles. And with this definition, this 2 times P, that's effectively the number of stator coils. With this definition in mind, let's take a look at a more complex stepper motor. This motor has 8 total stator coils arranged in 4 stator coil pairs. As a result, this motor has 4 phases, so P is equal to 4, as well as 3 different pairs of poles on the rotor, so N poles is equal to 3. Thus, the total number of steps for this motor, that'll be equal to 2 times P times N poles, which will be equal to 24, or 24 steps. In terms of number of degrees that the rotor is rotating per step, that's equal to 360 degrees divided by S, or 15 degrees per step. In addition to the step performance of the stepper motor, another characteristic of the motor that's of great importance is going to be torque. And perhaps the most important torque value that you will see on a datasheet is the holding torque. The holding torque is the maximum amount of torque that can be applied to the rotor before breaking the position and rotating the rotor. And thus the torque that I can apply while driving the motor is typically going to be less than this holding torque. To apply a holding torque, we need to apply power to the coils of the stepper motor. So another important torque value to define here is what's called the detent torque. The detent torque is the amount of holding torque that the motor can provide when power is not applied to the motor. And this torque is a result of the magnetic attraction between the poles on the rotor and the poles on the stator. As a quick example of these torque values from a stepper motor, you might find a typical holding torque number on the order of 0.23 Newton meters, while you'll find a detent torque on the order of 0.016 Newton meters. So for this motor, the detent torque is an order of magnitude less than the holding torque, but it's still a significant amount of torque provided. Here's the model for a basic 2-phase stepper motor. Here we have the A and A prime coils in series together, as well as the B and B prime coils in series together. When we run a current in this direction, we can set up a particular stator pole, and when we run a current in the opposite direction, we can flip the polarity of that stator pole. Although there are a variety of winding configurations for stepper motors, this particular configuration shown here is what's referred to as a monofiller winding. In order to drive a stepper motor with this type of winding, we'll need to be able to reverse the direction of current, and we'll need to source a rather large amount of current to the motor. And this is typically more than a microcontroller, such as your Arduino, can provide. Because of these two requirements, a typical way of driving a stepper motor is to incorporate an H-bridge circuit. Now, we'll need a full H-bridge to drive each phase of the stepper motor, and this gives rise to the notion that the control circuitry for a stepper motor is typically much more complex than a basic DC motor. So here we have a dual H-bridge circuit that is configured to drive this 2-phase stepper motor. In this circuit, we have a full bridge on the left, and that bridge will drive the A and A prime coils. And we have a full bridge on the right driving the B and B prime coils, or the B and B prime phase. And we'll go ahead and label all of the transistors in the circuit T1 through T8. A typical mode of operation will have T1 and T4 on, so we'll get current flowing through in this direction. And in the case where we have T2 and T3 on, we'll get current flowing in the other direction. So we can set up a matrix looking at all of the transistor pairs and the performance of the motor when each pair is on or off. If we recall our previous slide when we were looking at the steps required to drive a stepper motor, we'll begin with step 1, where we're driving current through the A and A prime coils. And to do that, we will need to turn on transistor T1 and T4 while leaving all of the other transistors off. As a result, we'll get a current flowing in this direction. The next step was to turn off the current through the A prime coils and turn on the current through the B and B prime coils. So to accomplish that, we'll turn on the transistor pair T5, T8 and turn everything else off, and as a result, we'll get a current flowing through B, B prime in this direction. The third step required to drive this two-phase stepper motor was to drive a current through A prime and A in the opposite direction as step 1 here. And to accomplish that, we'll turn on the transistor pair T2, T3 while leaving all of the other transistors off. And as a result, we'll get a current flowing through A prime and A. And then finally, we need a current going through B prime and B in the opposite direction as step 2 here. So we will go ahead and turn on the T6, T7 transistor pair, leaving everything else off. And as a result, we'll get a current flowing through the coils from B prime to B. And then this cycle would repeat 1 through 4. So this allows us to achieve this stepper motor operation that we had previously explored, in this case 4 steps for a 2-phase motor, by using a dual H-bridge circuit. In terms of complexity, obviously if you have more phases or more poles in an attempt to get even finer step increments, the circuitry complexity increases dramatically. Let's wrap up this lecture with a quick look at a unique application of stepper motors. Shown here is a wind LiDAR, an atmospheric LiDAR that flies on a high-altitude UAV. And this particular LiDAR, due to thermal gradients across the instrument from takeoff up to altitude, needs to be aligned periodically. So to accomplish that alignment, we built a tip-tilt mirror into the system. So this piece of glass here is a mirror for ultraviolet wavelengths. And this mirror rotates about 2 axes. We have a vertical axis and a horizontal axis. To achieve that rotation, the assembly has 2 linear translation stages attached to 2 flexures, and in each stage from Physics Instrumente is a linear actuation assembly comprised of a stage, a lead screw, and a stepper motor. So because this alignment process is happening periodically through flight, we're particularly interested in the detent torque of this stepper motor and ultimately this ability of the linear stage to hold and maintain a particular position and keep the mirror in alignment throughout flight. Also of particular importance for this assembly is the precision in steps for the stepper motor, and thus the precision in linear translation of the stage. This ultimately defines how well we can align the laser beam exiting the instrument with the axis of the telescope in the receiver. Thus, for this particular application, using a stepper motor in a linear translation stage, we were primarily interested in the specifications such as max holding force to be able to hold that position of the mirror throughout flight, as well as the minimum incremental motion. The minimum incremental translation of the linear stage, which is a direct result from the minimum incremental rotation of the stepper motor, and that ultimately drives the minimum angular displacement or rotation that we could achieve with the mirror, thus defining how well we could align the transmitter to the receiver of the wind LiDAR.